So today we're going to be looking at some of the features in Immunity Debugger that make it easier to write and generate ROP payloads. On another virtual machine, I have a malicious web server running through Canvas's client D, and that's going to be serving up a slightly modified version of our IE peers set attribute exploit. Basically, this exploit is a use after free, and one of the first things that we're going to want to do is disable depth for a given page on the heap, and then return into that. So first we simply attach to the process. And continue. So we can see at this point the program has crashed while trying to execute 41, 41, 41. By looking at the backtrace, we can see that the cause of this essentially was ECX was treated as a vtable pointer. We retrieved the offset +1c from that. And we can see there we have replaced that function pointer with 41, 41, 41. The heap spray, etc. is already in this exploit, so what we're going to do now is just focus on how we go about first swapping out ESP with a pointer to memory on the heap that we control, and then this pointer, or this heap memory, will essentially be our sequence of return addresses for our ROP payload. How this is normally done is by looking for something that exchanges a pointer to this memory on the heap with the ESP register. So you can do this manually by hand by building a gadget state, a list of gadgets from a DLL. I'm simply choosing secure32.dll here because it's small enough to complete for the purposes of a demo. This normally takes about 30 seconds to a minute. So we can see at this point that the Python script has essentially found every ret in that DLL and then walked backwards to find candidate gadgets. So for example, in this case, pop ESI, pop EBX, leave ret14. What we're looking for here is something that's going to swap the ESP register with one of the other registers or a dereference from that register that points to heap memory that we control. So if we start going through these registers, starting with EAX, follow and dump, which displays the memory on the heap that this points to, and we can see here that this essentially looks like an object that we may control. Unfortunately, in this case, this isn't big enough to fit our payload and the required values, but we also control these values. So if we follow the first 4 bytes, we can see that this again, we've constructed a point back into the heap again. And at this point, we have the start of our ROP sled, a sequence of essentially NOPs, and then starting from here, we have our shellcode. So what we want to do is we need to swap ESP with not EAX, but the value pointed to by the memory at the location that EAX itself points to. So essentially a dereference of EAX, and the value there needs to be swapped into ESP. Doing this by hand can take time, so essentially one would go through these candidate gadgets, look for something that swaps ESP with EAX, and then pops that value into ESP, and then returns. So you get the idea. One of the features of Immunity Debugger at the moment, as part of deplib, is that we've essentially automated this process through the find pivot script. This script takes a database which is constructed from one or more DLLs and an expression that we want satisfied. So in this case, I've already pre-constructed a database for the DLL MSCTF GFIME.IME. And if we remember from earlier, essentially the expression that we want our gadget to satisfy is that it swaps the memory pointed to by EAX into ESP. This expression can be essentially any valid Pythonic looking expression that is over the registers or dereferences of the registers. So for example, mem EBX plus 4 would look for a gadget that will swap the value at EBX plus 4 dereferenced into ESP. So for our case, we just want the dereference value of EAX in ESP. That completes quickly. We can see here that we have two gadgets found, one found using our exact searching and one found using the heuristic searching. So if we look at the first gadget found, it's essentially exactly what we need. We have an exchange of EAX with ESP, a pop into ESP, and then a ret. So if we set the origin here, essentially what we're hoping for is that the ESP after this gadget will point to a page on the heap that we control, at which point we can fill in the rest of our depth disabling ROP return addresses. So if we single step, we've now exchanged EAX with ESP, popped the value that was there into ESP, and at this point we can see that our stack window now displays memory that's on the heap. With already we've preloaded the return address to virtual protect and the arguments to that, and then we have a return address that's going to leave us back in this same page. So if we single step again, we can see now we're coming up to our virtual protect call, and from this point onwards it's essentially just a matter of constructing the rest of our ROP payload here as we wish, or in this case we simply call virtual protect, change the permissions on the page, and then return back into our shellcode. If, for example, we needed to do other things in our ROP payload, for example, we wanted to set particular registers, or we wanted to move particular values into particular memory locations, we also have other scripts in Immunity Debugger to do this. So one of the script is find gadget. Find gadget takes the pickle file returned by the bang gadget script earlier. Then it takes a sequence of arguments that essentially specify the semantics of the gadget we're interested in. So for example, if we wanted a gadget that takes EAX as a destination, moves the value OX0 in there, and preserves the ESI register. We can search for that. And it gives us back a gadget. If we pass the -A option, it would find all gadgets that complete this operation. So in this case, we can see that it's found a longer gadget than necessary first of all, but we could take, starting from here, We've an XOR of EAX with EAX, a leave, and a ret4. So essentially we can search for arbitrary gadgets in this way. We can also specify source registers, so we could say EBX here, which would look for a gadget that swaps EBX into EAX. Or again, we can have expressions like EBX plus 4, and this is the same on the source. We can search for example, the dereferenced destination EAX, and then a value OX0, and so on. All of these scripts are essentially based on the deplib backend. We have a number of other scripts as well that are based on the same x86 to SMT conversion engine. So for example, we have varbound, which takes a number of arguments, like a start address, an end address, an output register, and input registers that we control. In this case, what it will do will start at a starting address, run until an ending address, and at the end address give you the total possible values that the output register could have. This is useful, for example, if you want to treat a chunk of assembly code as a black box or whatever. We also have simexec, which, given an input register and an output register and a value or a relation between those two that we want, between the output register and a value, it will give an input to the input register that will result in that value in the output register. And then we also have more experimental scripts, for example, find int overflow. The final goal of which will essentially be to find integer overflows in blocks of assembly code. For now, it just handles the add instruction, and it's quite primitive in many ways, but we're hoping to work more on that. And there are several other scripts that are shipped in the current distribution of Immunity Debugger. If you're interested in the source, you can check out in the PyCommands directory. There's a deplib directory and an x86 SMT directory that contain these scripts. And also the library backends are in libs/deplib and libs/x86 SMT. For any questions or comments, you can email immunitydebugger@immunityinc.com. Thank you very much.